We are venturing into AI again without knowing much about it, just to piss off the people who keep telling me that I shouldn't be talking about things I don't understand. But the trick is to read, understand, and especially things that are inevitable, like AI in our business, climate predictions and climate projections, improving climate models, etc. It's unavoidable, so we better be aware of what's happening. This is a nice paper that talks about a foundation model for the Earth system. Why is this exciting? If you read the definition, you will understand. What is a foundation model? This comes from this blog here, humanloop.com. Foundation models are large neural networks trained on large amounts of unlabeled data, so you don't tell it what it is, don't annotate it. Unlike more narrow traditional AI models, foundation models are general purpose and can be easily adapted to many different tasks without new training data. Examples of foundation models include large language models like GPT-4, Claude, and Llama, as well as large-scale image and audio models. So you train it on a data, and then it learns enough about patterns, and in our case of the Earth system, has to learn about the physics of what drives the patterns, etc. And then you can apply it in another situation where it hasn't seen any data from that system, and can still, the two systems have to be related in some way, obviously. In our Earth system, it will be like applying a foundation model for the ocean, for the atmosphere, for pollution, weather. So, very different things. Now you know why that's exciting. Instead of improving specific models or Earth system model itself, you have a foundation model which is fully AI model, and then you apply it obviously for good measure. The paper also shows some examples of how they are doing better than the dynamic model against which they are comparing their forecasts and simulations and so on. So reliable forecasting of the Earth system is essential for mitigating natural disasters and supporting human progress. Traditional numerical models, although powerful, are extremely computationally expensive. Recent advances in artificial intelligence have shown promise in improving both predictive performance and efficiency, yet their potential remains underexplored in many Earth system domains. It's just the beginning. Here we introduce Aurora, a large-scale foundation model trained on more than 1 million hours of diverse geographical data. What does that mean? You have global data, but also time series. Aurora outperforms operational forecasts in predicting air quality, ocean waves, which is very different from air quality, and tropical cyclone, another completely different problem. So tropical cyclone tracks and high resolution weather, all at orders of magnitude lower computational costs, which is a big deal, because if you're trying to make a cyclone forecast, your forecast has to be fast enough that you stay ahead of the cyclone by as much lead time as possible, so that you can issue the warning, alert, etc., and people can take action, right? So computational cost becomes very critical. With the ability to be fine-tuned for diverse applications at modest expense, Aurora represents a notable step towards democratizing accurate and efficient Earth system predictions. These results highlight the transformative potential of AI in environmental forecasting and pave the way for broader accessibility to high-quality climate and weather information. Let's read some upfront material, and then we'll just look at some examples from the paper and jump to discussion. Earth system forecasts are indispensable tools for human societies, as evidenced by recent natural events such as the floods in Valencia, the air quality crisis in New Delhi, and Hurricane Helen and Milton in the eastern United States. You can think of zillion examples. Such systems not only provide crucial early warnings for extreme events, but are also important for diverse applications applications ranging from agriculture to healthcare to global commerce. Modern Earth system predictions rely on complex models developed using centuries of accumulated physical knowledge, providing global forecasts of diverse variables for weather, air quality, ocean currents, sea ice, and hurricanes. And we have gone, from climate models to Earth system models because we convinced ourselves that feedbacks between the carbon cycle and the climate, and vegetation and the climate, and human activities and climate are all important, so we must all include them. But complexity doesn't necessarily mean better accuracy. So maybe foundation models bring a different approach to solving this very complex system and making predictions, right? Despite their vital role, Earth system forecasting models face several limitations. They are computationally demanding, often requiring purpose-built supercomputers and dedicated engineering teams for maintenance of the model itself. Their complexity, built up over years of development by large teams, complicates rapid improvements and necessitates substantial time and expertise for effective management. In fact, if you found a great way to improve the model, you won't be able to immediately go and change the model because it's often frozen in time because the forecast system is running and they have cycles at which they upgrade the model, so you can't change the model day to day. Finally, forecasting models incorporate various approximations such as those for subgrid scale processes limiting accuracy. Basically, I won't go into details because I have discussed it elsewhere. These challenges open the door for alternative approaches that may offer enhanced performance. Machine learning provides an attractive toolbox for addressing these issues. Breakthroughs in numerous fields have shown that complex prediction systems can be streamlined with machine learning models that deliver superior outcomes. We have already discussed the Google model and other models, AI models, which have improved forecasts and are faster, etc. This concept was introduced to the earth sciences as early as the 1990s with pioneering work on neural networks applied to various earth forecasting problems. However, these early models could not scale to replace full dynamical systems. In 2023, I think somebody may be knocking at my door. Let me check. I thought I heard some noise, but maybe I was mistaken, or maybe the cleaning person comes and I ask them not to ring the bell, because if I'm recording, the bell shows up very loudly in the recording, so I ask them to knock. But then I'm wearing headphones and talking, so maybe I don't hear sometimes, but either way, I've messaged the person. So all these life's problems, I need AI to solve these. Okay, where were we? Yeah, so obviously the early neural network models didn't quite succeed because they could not scale to replace the full dynamical systems. In 2023, a breakthrough came from Pangu weather, in which a neural network replaced a numerical solver, outperforming state-of-the-art forecasting systems and sparking a wave of weather prediction models based on AI. These advancements have mostly centered on global medium-range weather forecasting at 0.25 degree resolution, leaving substantial gaps in other areas including ocean dynamics, wave modeling, and atmospheric chemistry. So AI models have focused on weather forecasting, physical weather, and extending the time scales of that, and not necessarily building a foundation model that can do weather forecasting as well as air chemistry and ocean dynamics, cyclone tracks, and so on. Okay. Furthermore, the potential for machine learning to outperform complex extreme weather prediction systems, which at present rely on human analysis of a wide range of models, remains underexplored. In this paper, we introduce Aurora, a foundation model for the Earth system capable of tackling a variety of forecasting tasks, taking inspiration from recent successes of foundation models in other fields. We first pre-train Aurora on more than 1 million hours of diverse Earth system data. We then fine-tune the model on a range of downstream tasks, demonstrating for the first time that an AI model can outperform several existing operational systems while also being orders of magnitude faster. Specifically, Aurora achieves state-of-the-art performance in the following critical forecasting domains. So I'll show a couple of figures to get an idea of what they're talking about. 5-day global air pollution forecasts at 0.4 degree resolution, outperforming resource-intensive numerical atmospheric chemistry simulation on 74% of the targets. Obviously, it can't be 100% better all the time, but nonetheless, 74% in the test cases is great. 10-day global ocean wave forecasts at 0.25 degree resolution, exceeding costly numerical models on 86% of the targets. The resolutions are important because that corresponds to the computational cost of global dynamical models to do the same thing. 5-day tropical cyclone track forecasts outperforming 7 operational forecasting centers on 100% of the targets. 10-day global weather forecasts at 0.1 degree resolution, surpassing state-of-the-art numerical models on 92% of the targets, while also improving performance on extreme events like heavy rains and heat waves, etc. So Aurora, briefly, an Earth system foundation model. Aurora is a machine learning model that produces forecasts for any collection of Earth system variables at any desired location. So it's not just weather. The model consists of 3 parts: an encoder that converts heterogeneous inputs into a universal latent 3-dimensional representation, a processor that involves the representation forward in time, and thirdly, a decoder that translates the standard 3D representation back into physical predictions. Okay, the processor is implemented as a 3D swin transformer, a 3D swin transformer, and both the encoder and the decoder as perceiver-based modules. We are getting very technical here. We'll look at a figure and just try to understand as much as you can, because honestly, if we want to use the products of this model or run this model if it becomes available, we don't need to know all the nitty-gritty, just like we run the dynamic models at global scale or regional scale without necessarily knowing all the details. We need to know enough to make sure we are doing the right thing and not misinterpreting things, of course. Forecasts for different lead times are generated by recursively feeding predictions back into the model as inputs. So you have an iterative process which is not exactly the same as a dynamic model. For a detailed discussion of the model, there is a supplementary information. We train Aurora on a large body of Earth system data to learn a general purpose representation of the dynamics that govern atmospheric and oceanic flows and the associated second order processes like advection of pollution and cyclones, etc. This first training phase is called the pre-training and includes a mixture of forecasts, analysis data, and reanalysis data and climate simulations. You can see the supplementary figure for details. After the model has been pre-trained, a second training phase can make use of the learned general purpose representations to efficiently adapt to new tasks, new data sets, and new variables. This second training phase is called fine-tuning. Whereas pre-training is expensive and requires large amounts of data, fine-tuning is much cheaper and can typically be performed with little data. So you do the hard work, keep it ready, and then do the fine-tuning for specific applications with very little data. That's where computational economy comes compared to dynamic models. We primarily pre-train on atmospheric data because this is one of the largest sources of information about the dynamical processes underlying the Earth system. Concretely, the pre-training objective is to minimize the next time step, so 6-hour lead time. Every 6 hours they are making a forecast, just like most weather forecast systems, and mean absolute error for 150,000 steps on 32A100 graphics processing units, GPUs, which are large in numbers, so efficiently models can be parallelized and run, corresponding to approximately 2.5 weeks of training. Okay, so let's read it again without breaking. Concretely, the pre-training objective is to minimize the next time step mean absolute error for 150,000 steps on these GPUs, corresponding to approximately 2.5 weeks of training. Aurora is able to achieve unprecedented performance in fine-tuning tasks by simultaneously scaling the volume of data used during pre-training along with its model size. To evidence this scaling, we demonstrate that pre-training on more diverse data systematically improves validation performance as more datasets are added, especially for extreme values. So again, look up the supplemental. Oops. Yeah, I just kind of cut it off because the rest of the text was just more description. So let's just jump to the figure. Aurora is a 1.3 billion parameter foundation model for the Earth system. What does this mean? Basically, it's a statistical model. It's a foundation AI model. So deep neural networks, as we saw in the initial definition itself. There are details as you see here, but essentially they are just parameters fit to data so that the model knows what happens when things change, when you integrate or start the forecast from the initial conditions going forward, whether it's atmospheric circulation, extremes, cyclones, atmospheric pollution, or wave dynamics and so on. Okay, so times t minus 1 comma t. So 3D perceiver encoder, we talked about 3 steps. So arbitrary variables, pressure levels and resolutions fed into the latent atmospheric input and fed then into 3D swing transformer unit plus LoRa that we mentioned. Latent atmospheric output coming out of the second step, and then 3D perceiver decoder, which again produce arbitrary variables, pressure levels and resolutions for the actual forecasts at time t plus 1. So you're going from t minus 1 to t plus 1, which is the forecast. You can think of this as 6 hours prior to time 0 and time 0 and then 6 hours ahead. So Aurora Foundation model can do atmospheric chemistry and air quality, wave modeling, hurricane tracking and weather forecasting, which is the first such model to be reported. So icons are for illustrative purpose only. Aurora is pre-trained on several heterogeneous data sets with different resolutions, variables and pressure levels, because model outputs, reanalyses, data, everything come in different resolutions and time steps and so on, and different pressure levels. Model is then fine-tuned for several operational forecasting scenarios at different resolutions: atmospheric chemistry and air quality at 0.4 degree, as we mentioned, wave modeling at 0.25 degree, hurricane tracking at 0.25 degree as well, and weather forecasting at 0.1 degree. If you don't know what that means, weather forecasting at 0.1 degree is monumental. 10-kilometer global forecasting is really amazing, right? You can see this, the features, the fine features you see are only possible when you have such high resolutions. Aurora is a flexible 3D twin swing transformer with 3D perceiver based atmospheric encoders and decoders. Do we understand these in technical detail? No. Do we need to understand? If you want, you should pursue, but for me it just gives me enough understanding to say why this model will work and how I would use it. The model is able to ingest inputs with different spatial resolutions, numbers of pressure levels and variables, obviously, which means it's not like a dynamic model which is gridded regularly. There are irregular grid models as well, but I'll not show global maps here, but there are global maps given in the paper. This is an example of Aurora versus CAMS, which is an atmospheric model at 3-day lead time. So you can see the RMSC relative to CAMS. So CAMS is the baseline, and you can see that Aurora is lower for many of these variables at many different pressure levels. I won't read, these are different species of chemicals we are looking at for air pollution. At some point, and there are these that are worse than CAMS, and they try to explain why that is. This is why the model succeeds better than the original dynamic model in some 70-80% situations only, right? So in an operational setting, Aurora matches or outperforms CAMS in most comparisons at orders of magnitude smaller computational expense. Predictions for TCNO2 by Aurora accurately predicts CAMS analysis. Predicting atmospheric gases correctly is extremely challenging owing to their spatially heterogeneous nature. In particular, NO2, like most air pollution variables, is skewed towards high values in areas with large anthropogenic emissions, such as densely populated regions of East Asia. Also, NO2 exhibits a strong diurnal cycle. For example, sunlight reduces background levels of NO2 through a process called photolysis. Aurora accurately captures both the extremes and background levels. Aurora and CAMS forecasts are initialized with CAMS analysis on September 1, 2022 at 00 UTC. So I skipped the A and B, but we're looking at C here, which is what I just explained. Okay. C, at a lead time of 3 days, Aurora matches or outperforms CAMS on 89% of all variables. So you have 11% that are not doing better than CAMS. Okay, gives you a sense of how the Aurora foundation model is actually managing to do better than the dynamic model. So this is root mean square errors relative to a high resolution wave model. Again, you can see various variables. I won't bother to say what they are, but they are comparing relative to the HRES-WAM model at 0.25 degree and Aurora at 0.25 degree. Again, you can see mostly doing better, but then fails here. In an operational setting, Aurora matches or outperforms HRES-WAM in most comparisons. Aurora accurately predicts significant wave height and mean wave direction for Typhoon Nanmadol, the most intense tropical cyclone in 2022. Okay, I'm skipping the details basically because I want you to get a sense that people are really moving fast for using AI, especially a foundation model, not only for specific weather forecasts, but now foundation model means it can do all these examples that we are looking at. Okay, this is an example of cyclone forecasting. In an operational setting, Aurora outperforms state-of-the-art tropical cyclone prediction systems for several agencies and regions worldwide. Again, you get the sense that Aurora and the two data sets, IB Tracks is a data set, PGTW is another forecast given by various organizations. So you can see the 21st July, they're all, so this is at 12 UTC, 18 UTC and 00 UTC on 22, so 21 to 22, and obviously they are claiming that the Aurora is doing better, so the tracks must be better predicted by Aurora compared to the so actually it is observed is the IB tracks, and you can see Aurora closely tracks it as opposed to the PGTW models that are completely off. This kind of difference is not small. If you are trying to evacuate people and you tell people to evacuate here but it's going here, then obviously it's a big problem as well, right? So Aurora again attains better track prediction MAE than several agencies in various regions, and you can look up other details. There are some details as to exactly how the comparisons are done and why you have to be careful about what is being shown, etc. Aurora correctly predicts that Typhoon Daksuri will make landfall in northern Philippines, whereas PGTW predicts that it will pass over Taiwan. Okay, so you can see how different they are. Okay, so sorry, I'm being very brief. It's a very nice paper with lots of technical details and details on how fine-tuning is difficult for each of these problems. Let's just jump to the discussion. We have introduced Aurora, a large-scale foundation model for the Earth system that outperforms several specialized operational prediction systems at a fraction of the computational cost. We demonstrate state-of-the-art results for air quality, ocean waves, tropical cyclone tracks, and high-resolution Weather forecasting, from start to finish, each fine-tuning experiment took 4 to 8 weeks with a small team of engineers, compared with a typical development period of several years for dynamical baseline models. However, should be noted that such an accelerated timeline is only possible because of the wealth of data that is available as a result of decades of research into traditional numerical approaches, which is okay if you can exploit dynamical models to improve forecasts and make them faster. Then they can work together. Improvements are possible along several axes. First, Aurora can easily be extended to generate an ensemble of forecasts which are crucial in situations in which predictions are uncertain, such as for forecasts at longer lead times or for localized phenomenon. And usually you don't make track forecasts as just one realization. You tend to give a cone of uncertainty, as you may already know. So ensemble forecasts basically tell you that Mother Nature may go in one direction, but it has possibilities of going in many directions around that. Okay, from start to finish, we said that already. However, should be noted that this was possible because of decades of research. Improvements are possible, of course, by producing ensembles, which are crucial. Moreover, our scaling results indicate that we have not yet a performance ceiling, and that improved fine-tuning results can be obtained by scaling pertaining to more diverse data and scaling Aurora to even larger sizes. So as data keeps growing, Aurora should also do better and better by retraining and fine-tuning. Although Aurora is fully operational in all experiments, the model does still rely on initial conditions from traditional data assimilation systems, which are also very expensive but necessary right now. Following recent advances in end-to-end weather forecasting, Aurora could be extended to directly operate on observational data as well, skipping the data assimilation step. We could also investigate the interpretability of Aurora, aiming to understand whether specific patterns learned by the model can be linked to physical processes. So there are explainable models and interpretable models. Explainable models are basically like a black box where it does something and gives you an answer, and often you have a simpler model to explain the results, whereas interpretations means you know exactly what's happening so that you can understand why Aurora did what it did in a physical world, right, in terms of physical processes. Potential implications of Aurora for the field of Earth system predictions are profound. Although in this paper we showcase the application of Aurora to 4 domains, it could be fine-tuned for any desired Earth system prediction task, potentially producing forecasts that outperform the current operational systems at a fraction of the cost. Some examples include predicting ocean circulation, local and regional weather, seasonal weather, vegetation growth and phenology, extreme weather modalities such as floods and wildfires, pollination patterns, agricultural productivity, renewable energy production, and sea ice extent. With the ability to fine-tune Aurora to diverse application domains at only modest computational cost, Aurora represents notable progress in making actionable predictions accessible to anyone. So we don't know other details, whether this will become a public access community model, or if it will remain a proprietary model so that you only get forecasts and not get to run it yourself for research or for improving it and so on. But anyway, this is a great paper at this time to read. Just, without being an expert, we know just how exciting this advance is, right? So let's leave it here.